Okay, good afternoon, everyone, and welcome to today's sponsored ABC webinar, Biogas Desulfurization Experiences with THIOPAQ Scrubbers. My name is Erica Marin, and I will be facilitating this webinar. And before we begin, I just want to thank PAQ for sponsoring today's webinar. Their sponsorship directly supports the ABC and our programs, so thank you. Before we start with the content, just a bit of housekeeping. You should already be able to hear me and see the slide titled Quick Notes. If you're hearing any echoes or your sound quality is bad, change the audio options in the GoToWebinar toolbar, which should be on the right-hand side of your screen. And if you're still having trouble, send the organizers a message using the questions section of the toolbar. And don't worry, we're also recording this webinar, so we'll send you both the recording and the slides tomorrow. If you have any questions throughout the course of the webinar, we encourage you to ask them at any time using the questions pod in the toolbar, and we'll handle all questions at the end of today's presentation. So it's wonderful to see that we have so many ABC members on the line. Thank you all for your continued support to make everything that we do possible. For those of you who aren't yet members, we're really thrilled to have you too. In case you're not familiar with the American Biogas Council, we are the voice of the US biogas industry. We represent about 330 organizations which reflect the entire American biogas industry. If you're not a member and you'd like to engage with us and help grow the industry and your business, please join the ABC through our website, americanbiogascouncil.org. So, thank you everyone for joining us. Now I will hand it off to our moderator, Patrick Surfass with the American Biogas Council, to lead you through this wonderful presentation we have for you today. Patrick, please take it away.
Awesome, thank you, Erica, and welcome everybody. You can see all the attendees rolling in here. We are expecting a record-setting webinar today. With over 500 people registered for this, and we're so glad that you could be a part of this. Obviously, PAQ has a lot of really great things to share with you. We're gonna turn over here really quickly to our speakers, but certainly encourage you all who are new to the American Biogas Council, please reach out to us, engage with us. There are lots of great companies like PAQ that are members of the American Biogas Council, and we want to work with you to help build more biogas systems, recycle more organic material, and turn it into renewable energy and great soil products. Today we've got Steve Boyle, who's the head of marketing for PAQ. We've got Martin Thielbard, who handles sales in the US east of the Rockies, and we've got Andrew Delgado, who handles sales in the West and also does some of their fabrication work. You'll be hearing from all of them today. They're going to kind of tag team back and forth here. So I'm going to step back and let them talk. And while they are talking, definitely ask your questions in the questions area of the GoToWebinar here. I'll be monitoring those as we go along, and then we'll handle the questions at the end, and we'll get to those, as many of those as we can before we run out of time. So please join me in welcoming our speakers from PAQ. I'm interested to hear more. And Steve, I think you're going to kick it off for us. Take it away.
I am. Thank you very much, Patrick, for the warm welcome. Hello, everybody. I'm going to kill my camera, so I'm sure you don't want to see any more of my face. And as you probably can already tell, I'm not from North America. I'm actually sitting here in Glasgow in Scotland, where it's tea time. So I hope this doesn't run on too long. So welcome from PAQ here in Scotland. Next slide, please. Okay, so this is the outline. I'm tasked with the job of giving a brief overview of PAQ. I'm sure that some of you have heard of us, but I will try to keep it brief. None of this first the earth cooled and then the dinosaurs came. And then I'll hand over to my colleagues and we'll go through the THIOPAQ process, look at some of the reasons why you would want to choose THIOPAQ, look at the engineering and fabrication side of things, a couple of case studies, a summary, and then we'll take on the questions and answers. So without further ado, next slide, please. Okay, so here's the corporate bit, which I will keep it relatively short, but hopefully relatively interesting also. That is a THIOPAQ sitting there on the right of the slide, so it's been correctly done. As head of marketing, if you think the presentation's rubbish, you can always blame someone else. I will run 10 miles. If you think it's great, tell me. Next slide, please. Okay, let's go. So PAQ is just over 60 years old. It was founded in 1960 in a place called Balk in Friesland, which is in the north of the Netherlands, and it's just about an hour north from Amsterdam for those of you who have traveled in Europe. So it's a small town called Balk, of which PAQ is the major employer. Over the years, we've obviously, as you can see from the map, we've expanded across the globe, first in China and then building up in Brazil, North America, Malaysia, and for Asia Pacific there in Kuala Lumpur. We also have an office in Thailand, and also Chennai in India. And you can see that we have a variety of production sites across the world, as well as laboratories and very important pilot facilities for what we do. It was founded by the PAQ family, and originally it was just building tanks, making tanks for farmers, for silos. And then the founder, Mr. PAQ, met with a couple of other guys, and they started to look at the possibilities of using bacteria. And then was born the idea of anaerobic digestion. And we've obviously moved on from there, from those very, very early days on our humble beginnings. And now we're 62 years old with more than 500 people. We have installations in over 60 countries, and PAQ is present in one way or another, often largely, in more than 3,000 places worldwide. Next slide. Okay, so the essence of what PAQ does is using biotechnology to clean wastewater and gas. And today we're going to concentrate on the THIOPAQ, the sulfur system. If you look very briefly here, you'll see that we genuinely are numerically the market leaders, but also we're the market leaders for the level of research and invention that we do. Major markets that we work in across the globe are the pulp and paper industry, especially packaging, the food and dairy industry, beer and beverage. I'm not going to read all of those through, but I'm sure many of you on the call here are from those industries, and municipal as well, of course. We concentrate on the removal of COD, desulfurization, which we're talking about today, and then of course nitrogen and phosphorus removal, and indeed sulfate removal. We also have a business, THIOPAQ, which is part of the company, which deals in the purchase and selling of elemental sulfur. PAQ have supplied more than 1,500 bioreactors worldwide. It was relatively recently we supplied number 1,500, which I'm very pleased to say was in the United Kingdom, which was a real celebration for us. So PAQ is the market leader for two main reasons: numerically, that's the maths, and also because of what we invent, which I'll touch on slightly in a few slides. Next slide, please. Okay, so this is my chance to do the head of marketing thing. If we can press the button one more time, it should come up. It's a little bit delayed at my end here. I'm so far. Okay, go back. Thank you. Okay, so our tagline, green before green was a thing. We came up recently with that because we felt that what PAQ does has always been green. But sustainability became much more of a thing globally, and it's an increasing thing now as all over the world, and all with our major customers are asking us, what are you doing sustainability? How can you help us with our sustainability? You know, most companies are employing people who are specifically responsible for sustainability. It's a big thing, and we're a big part of that, and so we feel that this tagline is very fair. Next. Okay, so we take nature and we do something with it. Okay, and all these references in anaerobic digestion, for COD removal, references ammonium removal, and for nitrogen, and desulfurization, which we're talking about today. This is about taking bacteria, and I like to describe it as we make little villages of them, which create the granules. More people call it the granules. That's the proper title, but I like to call it little villages about clever bacteria, which with some serious R&D and technology go into the tanks and they do their magic. So It's a natural thing. We're part of nature, and we like that. Next. Okay, so this is the timeline of the R&D and its success. The BioPaq UASB, which of course is upflow anaerobic sludge blanket, just in case anyone's not sure. Our first one was in 1981. It was actually in a paper mill in the Netherlands, still there. And then the next big move for us was the THIOPAQ, which we're talking about today. Then we move on through with the BioPaq IC, internal circulation, the Anamox, the U-Box for sewage, and the BioPaq AFR, which the eagle-eyed amongst you will spot the Ben & Jerry's blanket that's been applied to our reactor there. AFR is the anaerobic flotation reactor, which we call the chunkinator. Okay. Then we are the second most recent major innovation was the ICX, which is kind of a more flexible IC, enabling us sometimes to not entirely have a new reactor, but to replace an old reactor with internals, and could save a lot of money for those that don't want to do an entirely new reactor. So that has had flexibility and some design changes to the IC concept, and has essentially become a new product alongside the IC. Just very, very recently, we launched, literally a few months ago, launched what we call the BioPaq Rise, which is extending our expertise into 3D printing for use in anaerobic technologies. And that's really exciting stuff. Okay, so next. Now, it's not just that we invent the major parts of what we do, okay? It's also that there are services around it. And without taking too much time, I will briefly go through these. At the top left, you have the sensor track, which is a biosensor. It's a very cost-effective way to monitor and ensure the health of your reactor. We offer process support. We offer training courses, both electronically and physically. We do audits of the wastewater treatment plants. As I mentioned with the ICX, we can do the rebuilds. There's a picture of one there. Power Mix is our nutrients, which boost the health and performance of the bacteria, of the granules. Then we trade in biocatalyst all over the world, both buying it and selling it. We will upgrade the existing reactors, carry out maintenance, provide technical support, and with it, we have extensive lab facilities all over the world. There's a complete service around the main products of the reactors. Next, please. Okay, the final slide from me. We also have a joint venture with Shell, which of course is actually Royal Dutch Shell, the big Dutch oil company. This is a 50-50 joint venture to specially look at the desulfurization in the petrochemical industry. Okay, so in summary, PAQ is a 60-year-old company that's started with humble beginnings. It's spread all over the world, and with a variety of uses of smart bacteria and excellent technology surrounded by services, we've grown from those humble beginnings to be a major player in the market. So I hope that gives you a little bit of flavor of PAQ, and I'm sure you can always ask us further if there's anything you want to know. So I will hand over to, I think, Martin.
That's right. Next slide, please. Yeah, so PAQ is at the cutting edge of innovation. We spent about 9% of our revenue in R&D to come up with new technologies or improvements of existing technologies. And well, this keeps us advancing, and this makes that we have a great understanding of the technologies and can provide great service should there be any issues with any processes. Next slide, please. Now we'll get into the THIOPAQ process. I'll give a general introduction, and then Andrew will get into the details after that. Next slide, please. So sometimes we're called a biological scrubber. The THIOPAQ is called a biological scrubber. It's really not. It's it's a combination of a chemical scrubber and a biological conversion of the sulfide that is removed in the bioreactor, and then a physical separation of the sulfur that is produced, which is a solid, in either a settler by gravity or a decanter. Next slide, please. So the THIOPAQ process, or the roots of it, were developed in the mid 80s and late 80s in cooperation with the University of Wageningen in the Netherlands. And the first THIOPAQ was installed in 1992 at a combination of paper mills in the Netherlands. So that was the first plant, and I think it started up in 1993. And you see, it took a while before the technology really took off, maybe 10 to 12 years or so. But once it became clear that this was a real cost-effective technology for for removal of hydrogen sulfide from gases, which means from biogas, landfill gas, and even gas of the oil and gas industry, it really took off ever since. Right now, of course, there's many projects in North America for treatment of dairy gas produced from dairy manure. But before that, the initial, let's say, 10 to 15 years, the majority of the THIOPAQ installations were at high-rate anaerobic treatment plants. So basically, Steve already showed a little bit of it, anaerobic reactors that treat effluent of industries, and as well as a few landfills. But to date, probably about 2/3 of all the THIOPAQ installations are at industrial wastewater facilities. By now we have about 325 plants working, or some of them still in the construction stage, and treating a total of about 300 metric tons sulfur per day altogether. And there's by now 53 plants in North America. Next slide, please. Well, I think we all know why hydrogen sulfide needs to be removed. It's very toxic. It's very corrosive. That's another reason, and it also produces sulfur dioxide upon combustion. So there's environmental regulations to control emissions. Next slide, please. PAQ uses only naturally occurring bacteria. Almost all technologies that PAQ has developed involve bacteria, like the anaerobic reactors, the digestion process, the Animox reactor. It's also a process that uses bacteria to convert ammonia into nitrogen gas, and the THIOPAQ also, which uses thiobacillus bacteria, of which there are many kinds. We use a specific bacteria that is very salt-loving, halo-tolerant sulfide oxidizing bacteria. So halo-tolerant means salt-loving, and these bacteria don't need an organic material to grow. They get it from chemicals such as sulfur or sulfide. And these bacteria are very hardy. They can grow under very extreme conditions, depending on the type of bacteria that you isolate. In the right corner on the top, you see a bacteria, a thiobacillus bacteria, that excretes the elemental sulfur that it produces. So the little yellow bulbs, that's elemental sulfur. Next slide. Andrew will explain the process in more detail.
Yeah, well, thanks, Martin. Yeah, so the THIOPAQ process, it consists of 3 main process steps. You have a scrubber column, which is an absorber. You have a bioreactor, and a means of settling the sulfur in a physical separation device shown here is a settler. Next slide, please. So if we can scroll through some of the animation here, we can kind of follow the pathway of the hydrogen sulfide. So coming in with our biogas containing the hydrogen sulfide, the biogas flows up through, if we can advance the animation, please. The biogas flows up through the PAQ column, and then there is countercurrent liquid stream that washes the hydrogen sulfide in to the liquid stream, and then it ends up as hydrogen sulfide in the bioreactor. And the bioreactor is really where everything takes place, kind of the magic of this process. So what we're doing in the bioreactor is converting the hydrogen sulfide into elemental sulfur, and then that elemental sulfur is removed in the sulfur settler. If we can advance the animation, please. And then the final disposition of that sulfur particle is removed from the settler and leaves the process. So that kind of gives you just kind of a rough overview of how, you know, the disposition of the sulfur as it moves through the process. It goes from the gas phase to the liquid phase as sulfide, and then to elemental sulfur, and then out as a slurry in the settler. Next slide, please. Next slide. Okay, if we can keep going with the animation. So the biogas, again, so I'm going to drill down a little bit into these 3 unit operations so you really understand what's happening here. Again, we have a water wash. We're taking the liquid stream from the bioreactor and flowing countercurrent to the biogas, which is flowing up. And the packing material, there's about 6 meters to 10 meters or so of packing material inside of the scrubber. This is the plastic rings that you see here. And this provides a high surface area to have the intimate gas liquid contact, so that mass transfer of the hydrogen sulfide into the aqueous phase of the sulfide readily happens. And this is an alkaline wash. So we call this, as Martin mentioned, this is chemical absorption. There's nothing biological going on here. It's all chemical. It's a caustic scrubber, and the H2S readily moves in to the aqueous phase when there is an elevated pH. So typically we're around 8.5, 8.3 or so pH. So the reaction here that you see is, of course, since it is a caustic scrubber, we are consuming alkalinity. And alkalinity is represented there as the OH minus molecule. So we take the hydrogen sulfide plus the OH minus, and that gives us the hydrogen sulfide, which comes out of the bottom of the scrubber, and now we're going into the bioreactor. Okay, next slide, please. So again, the bioreactor is the heart of the process. This is where all of our controls and automation, the scrubbing part is relatively easy. We're adding water to the top, and we're flowing the biogas, and that scrubbing happens very simply. In the bioreactor, you know, we have to make sure the conditions are just right for this process to happen. We want to keep the bacteria happy. So how do we do that? We need to add air, because air is part of the reaction. We need to have oxygen. There are air strings at the bottom of the bioreactor with diffusers that provide not only air and oxygenation to the bioreactor contents, but also some mixing. It's very important to note that the air that we add is completely decoupled from the scrubber, so we're not introducing any air into the scrubber. This just comes into the bioreactor and then out the top of the bioreactor as a spent or exhaust ventilation air, if you will. So in that vent air typically is very, very low in H2S, non-detect, and it just goes to atmosphere. Now, if you have some other organics or mercaptans, you may need to pay special attention to what you do with that vent air, because you may get some of those present in the vent air stream. But if we take care of the bacteria, then everything in the system will be very happy. And this bacteria, as Martin mentioned, is very robust. They can survive in very extreme environments. So what do we control in the bioreactor? Well, we control the ORP, and that's done by the addition of the air, or we have a blower that provides that air, and that runs on a variable frequency drive to control the ORP in the reactor solution. We also add water. Since we are adding caustic, we have to supplement with some of the alkalinity that we lose when we're removing the sulfur slurry from the stream. We do lose a little bit of alkalinity, so we have to replenish with sodium hydroxide. Generally, that conversion or recovery is about 93% or so. So we do have to add caustic. So when we add the caustic, we're increasing the salinity. We have to control the salinity, and the way we do that is by the addition of fresh water. There's also a blend of micronutrients that POC supplies with all of our installations, and that's to keep the vitamins, if you will, for the bacteria, to keep them nice and happy. So the key thing to note here is, and this is really the heart of this process, is what's outlined there in the orange box on the equation, and that is that we're producing the elemental sulfur so it can be easily removed from the process. And as part of doing that, we're regenerating the alkalinity. So recall from the previous slide, we're consuming that alkalinity, while in this process, we're producing that alkalinity. So the net effect is we get a very low operating cost, per pound of sulfur that we're removing. Okay, next slide, please. So the final step in the process is we've taken the H2S from the gas stream to the sulfide, and the bioreactor converted it from sulfide to elemental sulfur. Now we got to remove the solid from the process. So in this picture, we're showing a simple cone bottom settler. If we can advance the animation, we'll see some of the other devices that are used here. We can use a tilted plate separator to enhance some of the surface area, the settling characteristics of these particles, or we can use a centrifuge that will generate solids on the order of maybe 55 to 60% solids. And for our larger installations, we're generally going to use a centrifuge just because it makes the process more efficient, and we're just dealing with a lot of sulfur. And also this material, as Steve and Martin mentioned, it can be used as a fertilizer. POC has the FertiPOC business, and it can be used as a fertilizer, or more typically what's being done in North America is it's just being used as a soil amendment and discharged maybe in some aerobic lagoons and used to irrigate some of the fields. Okay, next slide, please. What can you expect as far as performance and reliability? Well, this process can take very high levels of hydrogen sulfide. We have installations that are taking H2S levels upwards of 20,000 ppm and higher. And we can get removals down to less than 25 ppm. Since it's a chemical scrubber, like I said, the absorption process happens very readily, and so we can get very good removals, and we monitor the alkalinity to get the levels of removal that we need, and also design the scrubber in such a way with particular packing height to get the right target removals for our customers. It's a very reliable process. There's not a whole lot of moving parts. We just have some rotating equipment. The circulation pump, which, like I said, just runs in a closed loop, delivering that wash solution to the top of the scrubber. And again, because we're regenerating the sodium hydroxide, the operational costs are extremely low. And as I mentioned, there is no dilution with air. The bioreactor, the oxygen that we add to the bioreactor is completely decoupled from the scrubber. I also wanted to mention that this sulfur that we're producing, it's hydrophilic, so we're not going to be seeing any plugging or anything in the packing. So it's very user-friendly. Operational costs are low with the high removal. Next slide, please. So what do you do if you feel like you have an application that you have hydrogen sulfide in your biogas? Well, you can call Martin or I. Our contact details, I believe, are in the slides here. And we'll talk to you about your application, and we'll send you a questionnaire. Sometimes we'll just fill it out with you on the phone and get some of the basics of your application. What's the gas flow rate? What's the H2S concentration? What are you looking for as far as treatment? Do you operate in a campaign mode? In other words, do you operate for a certain amount of time and then you're down for a couple of weeks? Or are you a manure dairy, a cow dairy where the cows don't stop pooping, we're just running all the time? We need to know this kind of information so we can configure our system to meet your specific needs. So we need that kind of information. Of course, we need all the characteristics, if there's any VOCs, is it a landfill, is it a food digester, CO2 concentration, oxygen concentration, and those types of things. So generally, we can turn a proposal around in a matter of a couple of days. So we look forward to getting some of your inquiries and seeing how this technology best fits your specific application. Next slide, please. Okay, so I'm going to turn it over back to Martin, and he's going to talk about some of the specifics as to why you should choose this technology.
Thanks, Andrew. Next slide, please. So why choose the THIOPAQ? Well, Andrew already explained some of the reasons. The major reason overall for most of our customers is and especially for RNG projects, is the lowest total cost of ownership for many desulfurization applications. Certainly when the sulfur load is more than, and this applies to North America, more than approximately 80 pounds per day, then the THIOPAQ scrubber already becomes attractive. In some countries, it's even at lower sulfur quantities. But this is mainly because of the low operating costs, because the biggest portion of the operating cost is usually the caustic, but because the caustic consumption is so low, it varies in the range of about 0.3 to approximately 0.7 pounds of 100% caustic per pound of sulfur removed. This of course helps tremendously. Also, and the process is very robust and therefore reliable. Our typical uptime is more than 98%, and this is also very important for the RNG market because of the very high value of the biogas, so that people want to get everything out of their biogas supply, and they don't want the hydrogen sulfide removal portion to interfere with that. Many plants also have greater than 99% uptime. We always recommend for if some greater than 99% is required, that the customer purchases high uptime spares, such as a spare aeration blower or a circulation pump and some other parts, so that things can be swapped out quickly should something happen, which is really rare with that equipment, but that you don't have to wait for weeks to get a new piece of equipment in. Also, question that's often asked is if we add oxygen to the biogas. Well, we don't, because we aerate the bioreactor, but the concentration of oxygen in the bioreactor is extremely low because we operate at such a very low redox potential, let's say roughly minus 350 millivolts. So there's no oxygen carried back with the liquid to the scrubber. So actually, at a plant where the oxygen is measured continuously, the oxygen concentration drops over the scrubber by a few hundred ppm. Then we achieve a very high removal efficiency, as Andrew already explained. Besides not adding air or not adding oxygen or even removing some, the process also removes a few percentage points of carbon dioxide that it absorbs and that gets stripped in the bioreactor. The system is very easy to operate. Then another slide will show the what's necessary for operation and maintenance. No hazardous byproducts are produced. The sulfur that is produced, it depends on whether you have a gravity settler or a decanter. Most applications just have a gravity settler. Then you produce a slurry and a bleed, and often these are, or usually these are combined. Then you get a liquid which is pumpable with 5 to 10% elemental sulfur, pH in the range of 8 to 8.5. It has a very high conductivity, about 45 to 75 millisiemens. And that's because it contains a lot of salts, mainly sodium bicarbonate at that point. So what we do at most plants, at industrial facilities, you typically discharge it to an aeration tank. For RNG applications, we have digester. Usually, it's one way or another. It's added back wherever the digestate goes to. You don't want to add it back to the digester itself, obviously, because you would cycle the sulfur up. But it goes back to typically to a lagoon, an aerated lagoon, or a regular non-aerated lagoon. So it ends up basically where it came from. And then for plants where you have a sufficiently large quantity, where you use a decanter, where you typically produce a cake with about 55 to 60% dry solids, this sulfur can be used as a fertilizer. Research has shown that the biologically produced sulfur is a better fertilizer than chemically produced sulfur. And that's why there's a market for biologically produced sulfur. And PAQ indeed can arrange the sulfur to be collected and to be used as a fertilizer. So again, the major region, or the biggest advantage of the THIOPAQ scrubber is the lowest total cost of ownership for many desulfurization applications. Next slide, please. So the process has been used for all kinds of different gases. So we started mainly at industrial wastewater treatment plants. Still about 2/3 of the number of plants are in those applications. You see the figure on the right. You see many in the pulp and paper industry, where they have biogas that often has H2S in the range of 1 to 2%, so 10,000 to 20,000 ppm. Also many in the food industry, beverages a little less, but altogether those are about 2/3 of our applications. The biggest market by sulfur quantity is the oil and gas market for us. Those projects are done through PAQ, because that requires a different meeting different standards that PAQ itself is less accustomed to. So those are handled through PAQL, which is based in the Netherlands, and it's a 50-50 joint venture between Shell and PAQ. So by so about almost half the sulfur load that is treated is from the oil and gas industry, and then followed by landfills, because there's also some very large, that can be very large and high sulfur concentrations in landfill gas. Next slide, please. Here's two examples of some extremes. To the left is a very small scrubber that only treats 20 pounds a day and 60 CFM. And I forgot where in which country that is, but still that was an attractive solution for such a small THIOPAQ versus another technology. In the US, we don't sell them this small. The smallest one would treat up to about 275 pounds sulfur a day, and from 200 to probably something like 900 CFM. So, and it would be overkill for such a small application. The largest one is in Korea, South Korea, the landfill. You see the big scrubber there, and it treats 20,000 CFM. Our scrubbers are, of course, if you hear caustic scrubber, you think of much smaller scrubbers probably. Our scrubbers are, of course, much larger because we operate only at a pH of 8 to 8.5. So the driving force for hydrosulfide to be absorbed is much smaller than in a traditional caustic scrubber, where you operate at pH of 11 or 12 or even higher. But because we operate at this low pH, 8 to 8.5, also we don't absorb all that carbon dioxide that consumes caustic. So that's the big advantage of operating at this lower pH. Next slide. Here you see some different examples of THIOPAQ installations. They all look a little bit different from what we typically provide in North America. The 4 and 13 ton per day units are at oil and gas plants. So in the US, we provide a more standardized system up to a certain treatment capacity, and so we typically provide the scrubber, the bioreactor, the container with all the process equipment, and then the technical services, the basic engineering, the P&IDs, etc. And for the small, so for the up to a certain load, we containerize the equipment. If the load or gas flow is higher, then we can not follow this approach anymore, and then also the process equipment is shipped loose. Next slide, please. This is a little bit about operating requirements, operating maintenance requirements. For typical installation, if you don't have a decanter, then it takes on average between half an hour at the most about an hour a day to operate and maintain the system. The consumables are caustic, which can be 50% or sometimes 20 or 30%, depends on the customer, and a nutrient solution, which PAQ provides. Utilities, water, which has to be below a certain hardness of 10 degrees German hardness, or 170 milligram per liter calcium carbonate per liter. Power, instrument air, and there's a heating and cooling requirement. We often want to cool the gas prior to the scrubber just to remove some condensables. Often we do that such that no heating or cooling of the processed liquid is required anymore. The THIOPAQ process is itself, the conversion of sulfide to elemental sulfur is exothermic, so it produces heat that well, if there's too much, that needs to be removed. Also the fact that you dissolve caustic in water, that produces some heat, that's an exothermic reaction. And the air that is injected into the bioreactor also is hot at that point and also produces some heat. So if you have a low biogas flow but with a high H2S concentration, then you might need cooling of the processed liquid. In very cold climates or in the winter, you may need some heating because of heat losses to the environment. Also, for startup of the THIOPAQ, you need to heat the water. The initial water needs to be heated to dissolve chemicals and to adapt bacteria to not get a cold start. Then the sulfur waste, I already said what the composition is. Sampling and testing, you see a sample to the right. Those are Imhoff cones. This is a test that's used a lot in wastewater treatment to see how many solids settle out. So that's a visual observation. We see how much solids settle out in a certain amount of time. We want to be in a certain range. That tells you whether you have enough biomass in your liquid and whether you should bleed more, so send more sulfur for disposal or send less. And you do that with based on timers. These adjustments are usually made no more than once a day or every few days. Also, the color of the liquid tells you if the process is working right and if the bacteria are happy or not. So there's some observation like that, and there's also a simple chemical test and alkalinity test, and sometimes a suspended solids test. So it's pretty straightforward in terms of maintenance, routine maintenance. Weekly, it's just the keeping the instruments clean and calibrated, especially the redox probes. Very important to clean those regularly and also replace them when needed. Otherwise, you risk adding too little air or too much air, and both are not good. Next slide. So if you compare the THIOPAQ scrubber to other technologies, there's many other technologies, but we check off all the boxes, we think, for the parameters to the left. We've seen some other technologies in the market as well. The scavenger and media and activated carbon systems, they tend to be economical for lower sulfur loads, we think above about 80 pounds a day, that the THIOPAQ is very competitive. We've seen bioscrubbers, but they tend to be more for very low sulfur loads, and where you don't mind to add air to the biogas, so not so much for RNG applications. Iron chelate, we've seen that more for higher sulfur loads, and in particular in the oil and gas industry. We don't know if the sulfur cake that they produce, if that's acceptable for agricultural disposal, because it might contain other chemicals that are used in the process. And we've also had some copies that are some competition of companies that like our technology very much and have tried to copy it, but most of them, or all of them, I I believe, not very successful. Next slide, please. And it's back to Andrew again.
Yeah, okay, thanks, Martin. I'm going to touch here a little bit on the engineering and fabrication aspects of the technology. So next slide, please. So when you buy a system from POC, you get a very detailed, comprehensive engineering package. It's really, kind of configured for, what the EPC contractor needs to do the complete upgrading process or the complete kind of biogas installation, whether it is upgrading or maybe pre-treatment for a cogen process or whatever. We don't do the installation ourselves, but we provide a very comprehensive engineering package for that. So what does that include? It's a very detailed mass and energy balance. You'll get a spreadsheet with a stream table. The stream table will have stream numbers that'll correspond to a process flow diagram, and you'll know the composition of that stream as you, all the way through the process. Of course, we're going to provide a P&ID for all of our equipment and our installation. The general arrangement drawings, you'll see here kind of a 3D rendering of kind of the basic, all the big components here. As we mentioned before, there's an equipment container, or this could be a skid. You'll see some slides here in a little bit, but that contains all of the, the circulation pump, instrumentation, and control panel, that sort of stuff. You've got the bioreactor, the scrubber. That white tank in the upper left-hand corner is a double-walled sodium hydroxide tank, which is heat traced and insulated. So everything you see here is designed to be installed outdoors. We have these in cold weather environments. We have them in warmer weather environments. But we provide all the general arrangement drawings so the engineer can do the detailed piping. So we'll work with your engineering firm to locate the nozzles, get everything oriented for your specific layout. What you see here is kind of our default layout in this arrangement. So we'd like to adhere to this, but we are certainly flexible for other arrangements as well. So we do the piping isometrics that's needed, but typically your engineer or your designer that's designing all the installation will do all that, so it's not necessary. We do, however, do all of our electrical schematics in our electrical package. So that includes all the wiring diagrams for not just the items that are installed, pre-installed inside the container, but also the devices that are outside of the container. There's some instruments on the scrubber and bioreactor, and also some field control valves. You're also going to get a very detailed O&M manual at the end that's going to have some operating and maintenance instructions for the operators. You're going to get copies of the submittals and individual O&Ms for the major equipment, the blower, the pumps, that sort of stuff, the data sheets for the instruments, and so on and so forth. Okay, next slide. Just some pictures of what the inside of the container looks like and some of the materials of construction here. To make the point, everything here is built in the US. We all to US standards. We use US made componentry, valves, major equipment such as pumps and blowers, instrumentation, everything that's readily available in the US and that you would expect to see in the type of project that you're developing. So that means, Anderson Hauser instrumentation, Gould pumps, Bray valves, that sort of stuff. So spare parts are readily available. You don't have to go searching all over the globe, and especially this, time when things are pretty hard to get, that simplifies it even further. So the container and the skids are manufactured and assembled in our shop in California. The tanks, the bioreactor, settler, and scrubber, they're all made out of fiberglass or HDPE. The fiberglass is typically made in the Midwest. Okay, so next slide. Okay, as far as the control systems, everything is fully automated. The operator does not have to sit there and look over the system to physically operate. What he does need to do is respond to alarms and warnings, but the system is fully automatic. We typically use Allen Bradley PLCs and have a user-friendly HMI screen that includes some multi-trends that allow us to kind of go in and trend. We have some preloaded trends that we can see some critical process parameters if we need to do some troubleshooting. In the upper right-hand corner, you see the control panel, and to the right of that is the instrument, what we call the sample loop. And as I mentioned before, this system runs as long as we are providing the correct environment for the bacteria. And what we're monitoring there, we're taking a slipstream from the bioreactor and we're monitoring pH, temperature, ORP, and conductivity. And the PLC takes those inputs and makes the proper adjustments to make sure everything is just how the bacteria want it. If we need more heat, we add more heat. There is a heat exchanger inside this container that was on the previous slide. So everything is pretty much set and ready to go. As Martin mentioned, the operations and maintenance really should be doing that visual check of the Eimhoff cone. That's one of the most important tests. It really tells us a lot. If the color is off, if the particles aren't settling the way they should be, if they're too big, if they're too small, that simple visual test tells us a lot. And then also some of this analytical data. And we'll provide you with a spreadsheet on startup and tell you exactly what parameters we'd like you to test for. And we'll look at that, as you need some support. We also like to have remote access to your installation or to our control panel via a VPN. So that way we can see exactly what the operators see, and our control systems come complete with an Ethernet switch to allow that connectivity to take place. You just need to provide the VPN connection. Next slide, please. Okay, I'll turn it back over to Martin, and we're going to wrap up here with some case studies.
Thanks, Andrew. Yeah, we have 6 case studies, but since we're already approaching almost 1 hour, we'll go through it really quickly. I always like to show this one. This was the first THIOPAQ that was built, the one that was put in service in 1993, the one that's at 3 paper mills. So it basically gets the gas from anaerobic reactor that treats effluent from 3 paper mills. And these reactors, these high-rate anaerobic reactors, you have to imagine these reactors have a hydraulic retention time, and this one has a hydraulic retention time of only about 6 hours or so, 4 to 6 hours, something like that. So the waste in those 6 hours, and especially because the water comes from 3 different production plants, the wastewater composition can change a lot, which of course affects the biogas flow rate and the composition. So we'll see slides how it affects the performance of the THIOPAQ. Next slide. This is a slide showing 11 years of operating data. So the H2S varies from roughly 5,000 to 10,000 ppm. Guaranteed value was 50 ppm. That's the red line there, and you see how the treated gas has almost continuously less than 50 ppm with just a few excursions in all those years. Next slide. Here you see a slide that biogas flow in over a period of 1 day. You see all these fluctuations because of the type of reactor that it comes from, the type of wastewater it treats. We get this question a lot too: how does the THIOPAQ handle variations in flow or H2S concentration? Well, here you see The flow varies from 150 CFM to 450 CFM. And you see the impact on the hydrogen sulfide concentration, which is the green line. So it doesn't have a problem with that. Next slide. As long as the sulfur load, of course, it's very important that the sulfur load doesn't exceed the maximum design capacity, at least not for too long. That's an important parameter. So this plant has seen an uptime of greater than 99%. Removal efficiency has averaged 99.7%, and the caustic use has been half a pound of 100% caustic per pound of sulfur removed, and that is what we typically see. It depends a bit on the type of biogas. It depends on the carbon dioxide concentration also, and the absolute concentration of hydrogen sulfide, but this is about an average half a pound per pound. So that keeps the operating cost very low. The design of the plants obviously is very different now, but this year was the first of its kind. Next slide. Here you see a THIOPAQ scrubber at a landfill in Quebec. The scrubber is, of course, the big vessel. It's an 8-foot diameter scrubber and 80 foot tall. It was designed to treat 6,000 CFM. It was started up in April 2019. The average flow has been 5,700 CFM. H2S in has been 917 ppm. I must say the design value was 1,300 ppm. The H2S out has averaged half a ppm, so very good results, very high uptime. That's also because they have a very qualified staff that operates the RNG plant here, so it gets excellent maintenance and attention here. Next slide. This is a graph of the H2S concentration going in and coming out since startup. The startup, you see the guaranteed H2S concentration of less than 25 ppm was achieved in less than a week. Now lately the hydrogen sulfide concentration in the landfill gas has increased to below or to above its design value, but you see how the THIOPAQ still dealing with it with no issue. So it's now treating 2,500 ppm instead of about 1,300 ppm. Next slide. And it's back to Andrew again.
Okay, I'm gonna run through these here fairly quickly. So I think I have about 3 or 4. So this is a large rum distillery. You can see it looks a little bit different because we have a train A and a train B. These are two 50% THIOPAQ systems. And as I mentioned before, turn down is an important requirement. This particular customer, they run the distillery in a campaign mode. So they run maybe say 90 days continuously, very hard, sending a lot of substrate to their digesters, producing all kinds of biogas, and then they're down for like 2 to 3 weeks, and with very, very little gas flow coming out of their digester. So this allows us to gain a little bit more turn down capacity, and the way we operate the system is kind of, you switch to train A during this off season, and then kind of go back to train B just to keep the bacteria happy and viable. So when they do start back up again, everything is ready to go and it ramps up real quickly. So the gas here is used as a fuel source to run their distillery boilers, saving tremendously on their fuel oil expense. Next slide. This is the manure dairy digester application in Oregon. The gas flow, these are the design conditions. So 1,800 SCFM with 2,000 ppm of H2S. This is an upgrading plant. There's an amine system downstream of this, and then it goes to gas compressors and into the pipeline. And then on the next slide here, if you can switch, we'll show you the data. And you can see here the design conditions, almost, very early in the startup, we started exceeding that 1800 ppm of H2S, or 2000 ppm of H2S. And so we upgraded this plant, or we expanded it, and we were able to do that simply by adding a blower. We had enough capacity in the bioreactor. It was initially a little bit oversized, and so we were able to give them a lot more capacity just by adding a second blower. So they've been running along here since 2019. You can see there on the right-hand side, even with that upgrade, they managed to exceed the H2S load. And what we heard was somebody had left a valve open or in the wrong position, and they were actually sending the removed sulfur from our process back to the digester. So they were cycling the sulfur, and all of a sudden the H2S concentrations in the biogas were getting very high, and then they realized it, and things came back down to where they were supposed to be. But all in all, very typical good performance from this system when they're operating it within the design conditions of the plant. Next slide. This next one is a dairy at an Idaho installation. Gas flow is about 1,000 CFM, 3,000 ppm of H2S. Again, these are the design loads. And similar to the Oregon installation, this is an upgrading project with a treated gas. CO2 is removed here with a membrane process, and then it goes to the pipeline. And next slide, please. This slide shows us the data. And you can see in the very early months there of startup, we were exceeding the design conditions, and then things kind of hit more of a steady state through the years of 2020 and 2021. And then there was some noise here. You see these peaks here to the right. We talked to the operators. Hey, what happened? Well, things aren't perfect, and you all need to be aware of things in your installations. But we found out what happened. That first big peak here is they ran out of caustic, and they couldn't get any caustic. There was an issue with the delivery. So this is what happens. If you run out of caustic, your alkalinity goes down, your performance goes down. But as soon as they realize it and take the corrective action, everything comes back to where it's supposed to be. The second peak, similarly, the caustic pump went out. These caustic pumps have short lead times, but however, they didn't have some of the critical spares that Martin mentioned earlier on hand. So they had to, I think, wait a few days to get that and get that caustic going back into the system. And then the noise there to the right, they were not running the system at the alkalinity that we needed them to. And so we actually visited the site, looked at their data and said, look, your alkalinity is too low. You need to get your caustic dosage back up. But you can see, 3 years or so of, very good data for this plant. Like I said, things work when the environment is correct. Next slide. And finally, this is an upgrading plant in California. This is a dairy cluster. So there's there's 4 dairies that contribute biogas from their digester, and it all goes to this centralized upgrading plant. And the THIOPAQ you can see there to the left, and then the rest of the upgrading plant there, a nice picture. And the gas flow here is 1,800 SCFM with 3,000 ppm design and a sulfur load of 657 ppm. So this again also goes to pipeline quality RNG. Next slide here, we'll show you the data. This installation just started up in last April, and we were very early on here operating already at design limits, pushing about 5,000 ppm where the design was 3,000. Of course, our biogas flow was a little bit lower than the 1,800 design at about 1,000, but if you take that with the higher H2S concentration, we were right at the 650 pounds per day mark, and you can see, very consistent removal performance there. And we talk to the operators regularly. They tell me they spend maybe half an hour to an hour a day operating the plant, and they have very good understanding of the operations and are learning every day and feeling very comfortable with it only after a short period of time of operating. Next slide. So that's all we have for you folks. Just to summarize, this is a well-proven technology, 30 plus years of experience. POC is the inventor of the technology. So that gives us the in-house experience. We've got 325 installations and counting. So we've seen everything, I think, to if something goes wrong, we know how to fix it. We know how to execute these projects, and we know how to apply the technology. We know when it works and when it doesn't work. So I'm sorry we ran a little bit over time here, but I think we have some time for questions. We appreciate everybody's attention, and please, if you have inquiries or you have a biogas application, we look forward to working with you to help your project be a success. So again, thank you for your attention.
Awesome. Thank you so much, Andrew, Steve, and Martin. Man, that was a great overview. I can tell by the we have a couple dozen questions here coming in that there's a lot of interest here. We've still got a couple hundred people on the line as well. So let's crank through as many of these questions as we can to try to answer those. And then I saw in the chat that you all said that you are more than welcome to get in touch with folks directly. So while we're doing the Q&A here, for those of you that have a really burning question, or maybe you just have something that comes up, go ahead and take down those email addresses there while we're doing this, and you can connect with folks directly. One of the things here, we had a couple questions in here about consumables, and I noticed that with one of your examples, you had about a half a pound of caustic that was being used. So I think you answered that one, but can you talk about how much water is generally used, and in terms of the sulfate oxidizing microbes in that middle step there, what kind of consumables do you have there? Can you quantify any of that or describe that?
Yeah, I'll try. Well, the water use depends a lot on the sulfur load, so it's a difficult one to answer. And I don't know exactly how much water is used per pound of sulfur removed. It's not strictly linear either. It depends on the carbon dioxide concentration and also whether you use a settler or a decanter. If you have a decanter, you use less water. But I'd say for most RNG applications or at manure, treating dairy manure, it's in the range of 500 to 1,200 gallons a day or so. That's fairly typical.
Thanks, Martin. And just a confirmed tip for everyone, we are planning to be able to share the recording here for this webinar to all the registrants, so you'll have access to that afterwards. Can you talk a little bit about if there's nitrogen in the gas that's coming in? Well, let me ask that one of these higher level questions first. Is the THIOPAQ system generally handling the biogas directly from the digester, or is it generally going through some kind of CO2 removal, and the THIOPAQ is more often taking the off gas from the product gas from the CO2 removal system?
Yeah. No, it takes the gas from the digester, so not after an amine unit, for example, but it can take it after an amine unit. Of course, then you have a smaller gas flow, but with higher CO2 and H2S concentration. But it certainly can do that. I mean, a lot of our applications in the oil and gas industry are like that, where we treat acid gas.
Thanks. And then for the water that the system ends up using, how do you recommend for folks? What is the quality of that water? What generally happens to the water from your system, and how do you recommend that the system is maintained to make sure that the water can be handled easily coming out of the THIOPAQ system?
So
yeah,
so the water that is I suppose they mean the bleed and the slurry, and those things are used intermittently. we need to control the conductivity of the liquid in the bioreactor. So we control the conductivity by adding water and disposing of water. Yeah, and and the total the combination, basically the slurry and the bleed basically have the same salt concentration but different sulfur concentrations. And especially for where you have a digester, that liquid is disposed of and combined with the digestate at some point. So after the digester, it's combined usually by sending it to a lagoon, where the digestate also discharges to. At industrial wastewater plants, it's typically discharged with the anaerobic effluent to an aeration basin.
Okay, so what about in the case of a landfill that doesn't have that those two options with the digestate lagoon or sending it back through the wastewater plant?
Yeah, landfills, we've seen landfills put it back onto of course then it's a smaller flow that you're dealing with, because almost all landfills, they take the sulfur out as a cake. So with that bleed, it's just mainly the water and not much sulfur, and then they irrigate the landfill with it sometimes. So they spread it on the landfill, or they have their own treatment plant, the leach treatment plant, where they send it to, or sometimes to a sewer.
Let's talk about the elemental sulfur that comes out. I assume that in most cases that is used as some kind of it's applied to the land, and it gets basically regenerated, as one of you were saying in the presentation. Are there any issues, like especially in Canada, for discharging that elemental sulfur into the ground and using it to contribute to soil quality?
Not that I'm aware of, but we only have like 4 or so plants in Canada. So 2 at landfills and 1 at a paper mill. And I don't think any of those applications that it's sent to for land application. So I don't know.
We do have we have an SDS of the sulfur, so we can provide you kind of the constituents, and the customers can send that to the authorities and have them have a look at it and see for themselves if there's something in there that may be of concern.
Let's talk about operations a little bit. There's some questions in here asking, what kind of people need to be assigned to the system, like how many shifts, do you need operators with certain skill level assigned to the system? Can you speak to that at all?
It's really fairly simple, but it's you have to. Well, I mean, it doesn't take much time, but you have to have a little bit of understanding, not even of the chemistry, but somebody who takes care of the plant, right? Just with wastewater treatment plants, for example, somebody who interprets the data, not just do the test, but also takes action if something looks different than what it should be. So somebody who really, does the tests and follows up if something needs to be adjusted. And so it doesn't need a very high level operator, and it's not even shifts. I mean, it's just a check once a day. Typically, these tests are only needed once a day, and often not in the weekend. We do that once the startup has been completed and you have some experience with it, and often it's done 5 days a week and not even during the weekend.
A lot of our operators, I mean, they'll be mechanics. They have a background of maintaining equipment. These plants have just a lot of rotating equipment, so they're lubricating, they're calibrating instruments, and this stuff is fairly straightforward to do. And that level of person, after we do the commissioning and startup, we train them on the basics of the chemistry. I mean, we're not looking for them to become experts, but we kind of give them the basics, the gotchas that where they could be in trouble. There's very basic laboratory testing that needs to be done. It's with HIOPAQ type equipment. All of this is very basic. Some other plants they do it with maybe a team, like they already have a lab on site. And the laboratory guy does all the analytical stuff. He logs in the data, and the other guys just look out after the mechanical, electrical, kind of maintenance. So it can be a combination.
Comment here, impressive lack of downtime for the system. So what might typically require the system to come offline, or for you to choose to take it offline?
There really is no scheduled major downtime, but often at plants they take a downtime of the entire facility for once a year or twice a year or so. In that period, we advise to do certain checks, like check the bioreactor aeration headers or influent headers if they are clean. If necessary, check if spray nozzles are flowing properly. But all these things can be done in, well, I'd say less than a day. But there's no planned replacement time for the packing in the scrubber, for example, because nothing grows in there just because of the conditions that are created. The bacteria don't grow on the packing, or the sulfur. The sulfur that's produced, like Andrew said, is hydrophilic. It doesn't stick to the packing. So, but only if you suspect problems, like if for some reason the performance isn't right and you expect something wrong in the scrubber, only then we would open up the scrubber. But otherwise, we don't.
What about any fouling of the system? Does that ever happen with either one of the different tanks that you all use?
It can happen if you operate under the wrong conditions. Under some conditions, you can produce what we call chemically produced sulfur. So if instead of producing sulfur that the bacteria produce sulfur, but that it's produced chemically, which can happen if you operate under at a very low sulfur loading, and then you can oxidize the sulfides chemically to elemental sulfur. Or if you just have a lack of biomass, you're not operating it as a biological, your reactor doesn't operate as a bioreactor, but basically as an oxidation tank, a chemical oxidation tank, then also you can create conditions that cause sulfur to stick on the packing. And
there are early indications built into the controls of this system to prevent those conditions. So if there's a lack of sulfur, the blower is going to turn down, to its minimum setting, and then when it gets there, you're going to get a high ORP alarm, and the operator, needs to take action, with that. And then also the pressure drop in these in the packing, we measure that, and that can be looked at and trended. And typically the pressure drop is very little. I mean, it may be an inch, maybe 2 inches of water column. So very, very low. And so all of a sudden, if the operator notices that it's, outside of the norm, he needs to be looking at things to try to do some investigation. So there are early indications to prevent anything like that from happening.
Let's talk about operating pressure and ambient temperature that's good for operations. There was someone who's asking, they said, we can experience like negative 32°C to plus 32°C temperatures. Can the system handle extreme temperature fluctuations like that, seasonal temperature fluctuations like that? And can you also give a sense of what the some of the operating pressures of the system are?
Yeah, it's so the bacteria, the bioreactor is typically maintained at in the range between 95 and 104 degrees Fahrenheit. So you do want to be in that range. If it's colder than that, the bacteria slow down. So you could run like that, but you know, these temperature ranges are quite common for us. Well, minus 32 is low. We have these plants in Canada that we have. They see those ambient temperatures. So you design for it. We can, in very cold climates, the bioreactor is placed inside, like you saw in the picture of that landfill, and the scrubber is insulated. At least certainly the bottom portion of the scrubber is insulated, or the entire scrubber. And of course, all the outside piping is heat traced and insulated. But the process, of course, has to stay at a certain temperature, preferably 95 to 104 degrees, and the rest is a matter of freeze prevention. And in terms of pressure, we have another landfill in Quebec. The scrubber operates at minus 200 inches water column. So that's one of the highest vacuums that we've done, I think. And in the oil and gas industries, there's a THIOPAQ, I believe, that operates at 75 bar. So 100 or 1,000 psi. But you know, that's just a chemical process. The bacteria don't see that that pressure. I don't know if it even affects them or not, but they're not affected by it anyway.
And I'll also point out that the containers, I forgot to mention, are there's HVAC. We insulate the ceiling and the walls. There's a heater. There's an air conditioner. So everything inside the container is under a controlled climate. So there are the chemicals. There's the micronutrients and an anti-foam tank as well if needed. So those chemicals need to be housed in the skidded systems. If you're in a very cold climate, that they need to be inside. That needs to be inside a building. But like Martin said, everything's when we have these systems in Idaho where it's very cold there, and as Martin mentioned, in Canada where in the Idaho installations, everything's outside, like you saw from the picture. In that case, the bioreactor is insulated, and and everything is otherwise weatherized.
Great. Well, thank you, gentlemen, very much for this. I think we're going to call it there. There are still even a lot more questions. I tried to kind of bundle as many questions as I could together there to try to get to as many of them as possible. I hope you all got a lot out of everything that was shared today. Again, the recording will be shared with you, and certainly you all have access to the contact information to our speakers and all the representatives at POC. We encourage you to reach out to them, and to our speakers. We'll give you all the questions that were asked. So you'll be able to see those and have the opportunity to follow up with people directly. Erica, any last words here before we sign off?
Just thank you everyone very much for attending. You will get an email with a survey, and also as soon as you close out of this window, there will be a survey that pops up. I would appreciate if you filled that out. And if you have any questions, feel free to contact ABC or any of the speakers. Thank you again.
Thanks everyone. Have a great day.
Thank you.
Thank you very much.
Thank you.